Today we're going to be talking about proportions and similar figures, so think back to your book Comparing and Scaling. We're going to be working with a lot of those topics and extending them just a little bit. Okay, so it's good for you to know similar figures, they're the same shape but not necessarily the same size. They could be the same size, but they don't have to be the same size. So I could pick like a triangle like this, and maybe that same triangle but smaller or larger. If I just made that grow, shrink, that could be a similar figure to each other. Okay, this little symbol, it's like a squiggle, kind of, or like the ñ in Spanish. That means is similar to. So if you see that symbol, it's going to mean similar to. In similar figures, corresponding sides are proportional, and I will show you what I mean in the next example problem, but that's always true. So here we go. In this figure, it says triangle ABC is similar to triangle DEF. So these two triangles are similar. Okay, so they're the same shape, different sizes. They're going to have the same angles. They're going to be in proportion to each other. Okay, so when I say corresponding sides are proportional, corresponding sides, they go in the order that it's written if there's that similar thing. So AB, this side, should be similar to DE. They should be proportional to each other. BC and EF, those ones will be corresponding. AF or AC, DF, those will be corresponding. So if I'm going to try to solve this problem, I can do it in a couple ways. I know they're proportional, so one thing I can do is I can set up a proportion. So a lot of options for setting up a proportion. I'm going to do longer leg over shorter leg in this case. So it looks like I'm going to go DE is 8 over 6. That should equal the same thing as in the other triangle, longer leg over shorter leg, x over 9. Okay, you've solved this many ways. Back in 7th grade, you probably looked for a scale factor, and I might look here. To get from 6 to 9, I'm multiplying by 1.5. So to get from 8 to x, I would also multiply by 1.5. These would be proportional, and I'm going to get an answer of x equals 12. And because this is a label of a measurement on a side, I'm going to call it 12 millimeters. Okay. All right, dilation is the actual shrinking or enlarging to create a figure. So just like that triangle I showed you earlier, I could do a semicircle or whatever. Okay, when I take a shape like this, and all I do is I stretch it out and I make it bigger and smaller, I'm dilating it. So dilation is the shrinking or enlarging of that. The scale factor is the ratio of the dimensions of the new image to the original figure. So like in that last problem, the scale factor from the little to small was 1.5. They were 1.5 times as big. The ratio of the dimensions of the new to the original, that's the scale factor. All right, we're going to look at scale factor on a coordinate plane and try to dilate an image. So we have a triangle DEF. It has vertices, so the corners of the triangle are -2, 2, 2, 1, and -2, 1. Or -2, -1, it looks like. It's dilated by a scale factor of 3. So that means the scale factor from the original to the new is going to be 3 times bigger. And the origin is the center of the dilation, so that's going to be our starting point, kind of. We're going to graph the original figure and its dilation on the same coordinate plane. So I have this coordinate plane. And I wrote these coordinates wrong because it's really a -2, -1 for that one. So the first thing you want to do is graph your original figure. So I'm going to do graph D at -2, 2. Call that D. E is going to be at 2, 1. And F is going to be at -2, -1. Okay, and it said it's a triangle, so it would be good of me if I can connect these points and make my triangle. And then I'm going to try to dilate it. I'm going to try to make it bigger by a scale factor of 3. So the easiest way to do this if you have a coordinate grid and you're doing it about the origin is to just simply multiply your coordinates by 3. And we call our image, we usually label them with a D and like a little mark, and we read that D prime. So if I multiply my coordinates by 3, I'm going to get them 3 times bigger. So I'm going to have D prime at -6, 6. E prime is going to be at 6, 3, and F prime is going to be at -6, -3. And if I graph this, now I have my new point at -6, 6. So I'm going to have to do a little bit of counting there, but that's, we call it D prime. E prime is going to be at 6, 3. So going over here, E prime. And then F prime is at -6, -3. Okay, and if I make this triangle, connect my sides, do the best I can. Maybe the easiest way to see that this is 3 times bigger, we can see that this is the length, and this, they all match. But it became 3 times bigger. Each of the side lengths became 3 times bigger. Now the area is 9 times bigger, but just the side lengths, 3 times bigger each. So that we call that the scale factor of 3. All right, you've seen this type of problem before. So the flagpole problems. A flagpole, we'll see my wonderful flagpole. Here it is, there's a little flag. It casts a shadow 102 feet long. So here's the shadow, it's 102 feet. Okay, and then here's this man over here. He's much smaller, maybe at least because the shadow looks smaller. Okay, he's 6 feet tall, and his shadow here is 17 feet long. Your job here is to set up a proportion and solve to find out how tall the flagpole is. So what we are looking at here, there's like the sun shining up here, and it's casting down its rays. And when you do the shadow with those sun's rays, and here's a 90-degree angle on the ground, these become similar triangles. So kind of like the problem that we had before, we're going to have a proportion that we can set up to solve these. So I'm going to call the flagpole, I don't know its height, so I'm going to call it x. We have lots of ways to do this, but I might say x over 102. So the flagpole height over the shadow equals the same thing as 6, the man height, over 17, which is the feet. Okay, and I'm going to try to solve this problem using some sort of an efficient method. I like to look for scale factor first and then cross multiply if it's not an easy number. So if I look from 17 to 102, if I divide 102 by 17, I find out that 17 goes into 102 6 times. So if I multiply 6 by 6, I can get x, or my height of my flagpole, which seems like it will be 36. So it looks like my flagpole is 36 feet tall. All right, let's look at this one, which is a map. Okay, if you're reading a map, a lot of times you see the scale of a map like written on the bottom of it here, and it says 1 inch represents 10 miles. So the map distance from Bulgaria to Gifford is 2.25 inches. How far is the actual distance? So again, you can solve this in many ways, but one way might be to set up a proportion that 1 inch represents 10 miles. So you want to know 2.25 inches, how much that represents in miles. Okay, it's always important when you're lining up your proportions that you make sure like the same measure goes on the top and the bottom. So we're doing inches over miles. We don't want to flip it. That would get us confused. So I look here to get from 1 inch to 2.25 inches, I'm multiplying by 2.25. So to get from 10 miles to x, I could also multiply by 2.25. And 10 times 2.25 is 22.5. And this answer is going to be in miles. Okay, I'm showing you one way to do these problems, but I want you to know that there's lots of different ways to set up proportions and to still get an equivalent answer. And I want you to find like a way that works efficiently for you. I like to use scale factor, but I know some of you like to use cross multiplying all the time. I like to use that sometimes. Okay, so what I want you to think about as you're like going home and talking to your parents or your friends or whatever, you're thinking about your math, I want you to think about how could you use proportions to find a distance that's difficult to measure. So for instance, like how tall a tree is, or the top of a building, or a distance across a lake, or something like that. How could you use proportions to find a distance that's difficult to measure? Okay, so that's your thinking question. Think about it. maybe come and tell me about that tomorrow. All right, I'll see you. Can't wait. Bye-bye.